Magnetization is transferred from an excited nucleus to an unexcited one if they are less than about 5 A apart. In other words, the effect provides a means of detecting the location of atoms relative to one another in the three-dimensional structure of the protein. Applications. The study of molecular structure, conformational changes, and certain types of kinetic investigation is the main use of NMR in the biological field. Most work is done in solution, and in order to eliminate solvent effects, the equivalent deuterated solvent for proton NMR would be used. The use of the technique in drug metabolism studies is of increasing importance, particularly when coupled with infrared and X-ray diffraction data, which can then be used in molecular modeling methods using sophisticated computer techniques to try to elucidate drug action. An examination of the scientific literature in the field shows a plethora of results for biological macromolecules using the whole battery of techniques described above. For peptide and protein structural studies, the species tend to be arbitrarily divided into those with relative molecular mass less than 15,000 and those between 15,000 and 30,000. Low resolution NMR has been obtained on the lab Professor Hetty's bovine pancreatic trypsin inhibitor (BPTI). High resolution protein structures for antiviral protein BDSL, the C3A and C5A inflammatory proteins, plastocyanin, theorexin, epidermal growth factor, and interleukins are some examples. The application of solid state NMR has been valuable in the study of, for example, Alzheimer's beta amyloid peptide and melanostatin. Much more specialized methods are required to extend the mass range beyond 30,000, but it is now possible and several antibodies have been investigated. A distinct advantage of NMR is its use in studying molecular behavior in solution. Any particular state is average, of course, but often produces more useful information than the constrained structures available from X-ray crystallographic studies. Results of studies of protein folding are exemplified by ribonuclease A, cytochrome C, bomis, alpha-lactalbumin, lysozyme, ubiquitin, and BPTI. The techniques have been applied to the study of enzyme kinetics both in vivo and in vitro. Amongst the groups of enzyme study are chymotrypsin, trypsin, papain, pepsin, dermalisin, adenylate, creatinine and pyruvate kinases, alkaline phosphatase, ATPase, and ribonuclease. Other examples are glycogen phosphorylase, dihydrofolate reductase, and triphosphate isomerase. Applications of nucleic acids includes not only a variety of structural studies of both DNA and RNA, but additionally investigations of interactions between various drugs and DNA and between binding proteins and DNA. Sequence assignments in oligosaccharides have been obtained, but work on intact glycoproteins has not been promising, particularly in multidimensional NMR, owing to the difficulty in decoding the data. Interactions between proteins and lipid bilayers in membranes have been observed, and the structure of certain membrane proteins has been related to the predicted biological function. Examples of such proteins are gramacydin A, bacteriorhodopsin, and rhodopsin, phage coat proteins, and alamedicine. The isotope 31P exhibits nuclear resonance, and NMR has been used extensively in studies of phosphate metabolism. The relative changing concentrations of AMP, ADP, and ATP can be measured and hence their metabolism studied in living cells and tissues. Intracellular and extracellular inorganic phosphate concentrations may be measured in living cells and tissues also because the chemical shift of inorganic phosphate varies with pH. The above list is by no means comprehensive, but it is intended to indicate the wide variety of structural, kinetic, and molecular dynamic studies that are now available. C4. Electron spin reversal spectrophotometry (ESR). Electron paramagnetic resonance (EPR) or electron spin resonance (ESR) is a spectroscopic technique which detects species that have unpaired electrons, generally meaning that it must be a free radical if it is an organic molecule, or that it has transition metal ions if it is an inorganic complex. Because most stable molecules have a closed shell configuration without a suitable unpaired spin, the technique is less widely used in nuclear magnetic resonance (NMR). The basic physical concepts of the technique are analogous to those of NMR, but instead of the spins of the atom's nuclei, electron spins are excited. Because of the difference in mass between nuclei and electrons, weaker magnetic fields and higher frequencies are used compared to NMR. For electrons in a magnetic field of 0.3 Tesla, spin resonance occurs at around 10 GHz. Quantum mechanically, an electron has a magnetic moment of micro B, the Bohr magneton. When placed in an external magnetic field of strength V0, this magnetic moment can align itself parallel or anti-parallel to the external field. The former is a lower energy state than the latter. This is a Zeeman effect, and the energy separation between the two is increment E equals G micro B D0, where G is the gyromagnetic ratio of the electron, the ratio of its magnetic dipole moment to its angular momentum. To move between the two energy levels, the electron can absorb electromagnetic radiation of the correct energy. Increment E equals H nu equals G micro B D0. And this is the fundamental equation of EPR spectroscopy. The paramagnetic center is placed in a magnetic field and the electron caused to resonate between the two states. The energy absorbed is dissosed monitored and converted into the EPR spectrum. EPR is used in solid state physics for the identification and quantification of radicals, i.e., molecules with unpaired electrons, in chemistry, to identify reaction pathways, as well as in biology and medicine for tagging biological spin probes. Since radicals are very reactive, they do not normally occur in high concentrations in biological environments. With the help of specially designed non-reactive radical molecules that attach to specific sites in a biological cell, it is possible to obtain information on the environment of these so-called spin label or spin probe molecules. An odd electron in an atom confers a magnetic moment to the molecule which can interact with an applied magnetic field. This interaction is the basis of ESR. An unpaired electron in such a magnetic field can exist in one of the following states. In a low energy state with a nuclear spin. Aligned parallel with magnetic field. In a high energy state, anti-parallel to the field. For conversion of low energy state to high energy state, electron absorbs appropriate quantum of energy. If electron is unpaired, it is possible to apply electromagnetic radiations to make spin reversal resonance if it occurs. Hv equals G beta H. Where beta is magnetic moment of electron, H is applied magnetic field, B is frequency. H is Planck's constant. In order to change from a low energy state to a high energy state, such electron must absorb the required quantum of energy. In the magnetic field of several hundred millikelvin, such nuclei absorb radiation in the microwave region of the electromagnetic spectrum, giving rise to the phenomenon known as electromagnetic resonance. The frequency of the radio waves absorbed during ESR depends on both the isotopes being studied and the magnitude of the applied magnetic field. ESR spectra are usually plotted as energy absorbed against the strength of applied magnetic field. Applications. ESR spectroscopy is one of the main methods used to study metal proteins, particularly those containing molybdenum, xanthine oxidase, copper, cytochrome oxidase, and copper blue enzymes, and iron cytochrome, ferredoxin. Both copper and non-heme iron, which do not absorb in the ultraviolet visible regions, possess ESR absorption peaks in one of their oxidation states. The appearance and disappearance of the ESR signals are used to monitor the activity in the multi-enzyme systems of intact mitochondria and chloroplasts, as well as in isolated enzymes. The appearance and disappearance of the ESR signals are used to monitor the activity in the multi-enzyme systems of intact mitochondria and chloroplasts, as well as in isolated enzymes. In metalloproteins, there exists a specific stereochemical structure whereby a characteristic number of oligons, frequently amino acid residues of the protein, are coordinated to the metal. ESR studies show that the structural geometry is frequently distorted from model systems, and the distortion may be related to biological function. Spin labels are stable and unreactive free radicals used as reporter groups or probes. The procedure of spin labeling is the attachment of these probes to biological molecules that lack unpaired electrons. The label can be attached to either a substrate or a ligand. Often the spin label contains a nitric oxide moiety. These labels enable the study of events that occur with a frequency of 10 7 to 10 11 s-1. If the motion is restricted in some directions, only an isotropic motion may be studied. For example, in membrane-rigid spin label in bilayers. Here the label is attached so that the no group lies parallel to the long axis of the lipid. Intramolecular motions and lateral diffusion of lipid through the membrane may be observed and measured. This study is achieved by either I concentrating the spin level lipids into one region of the bilayer, or E randomly incorporating, usually into model membranes. The diffusion of the spin labels allows them to come into contact with each other and causes line broadening in the spectrum. Free radicals are found in many metabolic pathways and as degradation products of drugs and toxins. Electron transfer mechanisms in mitochondria and chloroplasts involve paramagnetic species, for example the VS centers. Other redox processes involving the Flavin derivative SAD, FMN, and semiketones lend themselves readily to exploration by this approach. The G equals 2.003 signal is associated mainly with mitochondria, but different cell lines show different intensities. This phenomenon is also dependent on metabolic state. Factors that increase metabolic activity also lead to an increase in organic radical signal. Many studies have involved the free radical polymer melanin and the ascorbyl radical. The latter has been used to study the effects of certain drugs on sperm maturation. Carcinogenesis is an area where free radicals have been implicated and where their study has been of value. There is, in general, a lower concentration of free radicals in tumors than in normal tissues. Also, a concentration gradient is observed, being higher in the peripheral non-product surface layers than in the inner regions of the tumor. The free radicals may, of course, initiate the neoplasia. Chemical carcinogens are in many cases associated with generation of free radicals. An example is the prediction of carcinogenicity of certain polycyclic hydrocarbons. Polycyclic hydrocarbons arise by the successive linking of benzene rings along ring edges. Examples of such compounds are naphthalene 2 rings and anthracene and phenanthrene 3 rings. As more rings are added, the structures become increasingly complicated. As these compounds possess aromatic character, it becomes increasingly possible for the 3D1 nectar of the radical to be accommodated, i.e. these kinds of radicals become more stable and therefore possibly more long-lived. Many metabolic studies have made use of ESR. Examples of the metabolism of drugs, processes occurring in the microsomes of the liver, for oxidation mechanisms, and the free radical products of oxygen. Superoxide dismutase is scavenged oxygen-related dioxygenyl free radical 0. Nitric oxide, no, as an independent entity, operates as a physiological messenger regulating the nervous, immune and cardiovascular systems. It has been implicated in septic, toxic shock, hypertension, stroke and neurodegenerative diseases. Although no is involved in normal synaptic transmission, excess levels are neurotoxic. Another source of free radicals is the irradiation, for example with gamma rays, of biological material. For instance, S-cross linkages in proteins may be identified by irradiating the protein, and the free radical produced has a free electron localized in the S region. Another major application in this area is examining irradiated foodstuffs for residual free radicals. The technique can be used to establish whether the packed foodstuff has been irradiated or not. A similar biomedical, environmental application involves the study of hard biological materials such as bone or teeth. When such materials are exposed to ionizing radiation, energy is stored in them and this energy may give rise to the production of free radicals. Clearly, ESR may be used to detect these radicals and is used in dose assessment in nuclear radiation accidents. C5. X-ray crystallography. X-ray crystallography provides the finest visualization of protein structure currently available. This technique can reveal the precise three-dimensional positions of most atoms in a protein molecule. The use of X-rays provides the best resolution because the wavelength of X-rays is about the same length as that of a covalent bond. The three components in an X-ray crystallographic analysis are a protein crystal, a source of X-rays, and a detector. The technique requires that all molecules be precisely oriented, so the first step is to obtain crystals of the protein of interest. Slowly adding ammonium sulfate or another salt to a concentrated solution of protein to reduce its solubility favors the formation of highly ordered crystals. This is the process of salting out. For example, myoglobin crystallizes in 3 ammonium sulfate. Some proteins crystallize readily, whereas others do so only after much effort has been expended in identifying the right conditions. Crystallization is an art. The best practitioners have great perseverance and patience. Increasingly large and complex proteins are being crystallized. For example, poliovirus, an 8,500 kD assembly of 240 protein subunits surrounding an RNA core, has been crystallized in its structure solved by X-ray methods. Crucially, protein crystals frequently display their biological activity, indicating that the proteins have crystallized in a biologically active configuration. For instance, enzyme crystals may display catalytic activity if the crystals are suffused with substrate. Next, a source of X-rays is required. A beam of X-rays of wavelength 1.54A is produced by accelerating electrons against a copper target. A narrow beam of X-rays strikes the protein crystal. Part of the beam goes straight through the crystal, the rest is scattered in various directions. Finally, these scattered or diffracted X-rays are detected by X-ray film, the blackening of the emulsion being proportional to the intensity of the scattered X-ray beam, or by a solid-state electronic detector. The scattering pattern provides abundant information about protein structure. The basic physical principles underlying the technique are: 1. Electron scatter X-rays. The amplitude of the wave scattered by an atom is proportional to its number of electrons. Thus, a carbon atom scatters 6 times as strongly as a hydrogen atom does. 2. The scattered waves recombine. Each atom contributes to each scattered beam. The scattered waves reinforce one another at the film or detector if they are in phase, in step there, and they cancel one another if they are out of phase. 3. The way in which the scattered waves recombine depends only on the atomic arrangement. The protein crystal is mounted in position in a precise orientation with respect to the X-ray beam in the film. The crystal is rotated so that the beam can strike the crystal from many directions. This rotational motion results in an X-ray photograph consisting of a regular array of spots called reflections. The X-ray photograph. Shown in figure is a two-dimensional section through a three-dimensional array of 25,000 spots. The intensity of each spot is measured. These intensities are the positions of the basic experimental data of an X-ray crystallographic analysis. The next step is to reconstruct an image of the protein from the observed intensities. The image is formed by applying a mathematical relation called the Fourier transform. For each spot, this operation yields a wave of electron density whose amplitude is proportional to the square root of the observed intensity of the spot. Each wave also has a phase that is. The timing of its crest and troughs relative to those of other waves. The phase of each wave determines whether the wave reinforces or cancels the waves contributed by the other spots. These phases can be deduced from the well-understood diffraction patterns produced by electron density atom reference markers such as uranium or mercury at specific sites in the protein. The stage is then set for the calculation of an electron density map, which gives the density of electrons at a large number of regularly spaced points in the crystal. This three-dimensional electron density distribution is represented by a series of parallel sections stacked on top of one another. Each section is a transparent plastic sheet or, more recently, a layer in a computer image on which the electron density distribution is represented by contour lines, like the contour lines used in geological survey maps to depict altitude. The next step is to interpret the electron density map. A critical factor is the resolution of the X-ray analysis, which is determined by the number of scattered intensities used in the Fourier synthesis. The fidelity of the image depends on the resolution of the Fourier synthesis. A resolution of 6A reveals the course of the polypeptide chain but few other structural details. The reason is that polypeptide chains stack together so that their centers are between 5A and 10 apart. Maps at higher resolution are needed to delineate groups of atoms, which lie between 2.8A and 4.0 apart, and individual atoms, which are between 1.0A and 1.5A apart. The ultimate resolution of an X-ray analysis is determined by the degree of perfection of the crystal. For proteins, this limiting resolution is usually about 2A. C6. Atomic spectroscopy. All of the methods described above, with the exception of nuclear phenomena in the gamma and X-ray regions, have dealt essentially with molecular spectroscopy. It was indicated above that, in general, molecules give rise to band spectra and atoms to clearly defined line spectra. These lines can be observed by emitter's light, associated with a particular wavelength, which are atomic emission spectra or black lines against a bright background, which are atomic absorption spectra. Some elements, particularly metals, have an important role to play in biological systems, whether as simple cofactors in enzymes, the central atom in biological macromolecules such as iron and hemoglobin or magnesium in chlorophyll, or as toxic substances that affect metabolism. Use of atomic spectroscopy will enable data to be obtained that are important in understanding the biological roles of these elements. In a spectrum of an element, the wavelengths at which absorption or emission are observed are associated with transitions where the minimal energy change occurs. For example, the 3s 3p or D-line transition in the sodium atom that gives rise to the emission of orange light. When electron transitions occur in an atom, they are limited by the availability of an empty orbital level. An orbital level could not be orbital without contravening the Pauli exclusion principle. In order for energy changes to be minimal, transitions tend to occur between levels close together in energy terms. These limitations mean that emission and absorption lines are absolutely characteristic of the element concerned. At least for simple atoms, it is theoretically possible to deduce their electronic structure from their line spectra. The wavelengths emitted from excited atoms may be identified using a spectroscope, spectrograph, or direct reading spectrophotometer that uses detectors of the human eye, a photographic plate, or a photoelectric cell, respectively. In general, and in contrast to molecular spectroscopy, atom concentrations are not measured directly in solution. The atoms have to be volatilized either in a flame or electrothermally in an oven. In this state, the elements will readily emit or absorb monochromatic radiation at the appropriate wavelength. Usually nebulizers, atomizers, will be used to spray the standard or test solution into the flame through which the light is passed. Alternatively, the light beam is passed in an oven, through a cavity containing the vaporized material. Atomic absorption spectroscopy. Atomic absorption spectroscopy is based on volatilization of atoms in a flame causing them to absorb light of specific wavelength. Atomic absorption spectroscopy (AAS), in other words, is based on the absorption of light by free atoms. When the molecules come in contact with flame, their atoms get dissociated due to vaporization and absorb light of specific wavelength in ground state. Absorption lines are characteristic to atoms present in the compound. Atomic absorption spectrophotometer measures the absorption of beam of monochromatic light by atoms in flame. The number of atoms present in light path can determine the absorption of energy. In AAS, the wavelength of radiation emitted on volatilization of element in flame may be readily resolved in sample line spectra. The amount of radiation absorbed in proportional to the number of excited atoms present depends on the temperature of flame. Instrumentation. The main components of atomic absorption spectroscopy are: radiation source. The most commonly used radiation source to produce a beam of radiation with a narrow bandwidth or hollow cathode discharge lamp or white light with double monochromator. The hollow cathode lamp comprises of tungsten anode and a cylindrical cathode in a sealed inert gas tube. Utility of discharge lamp are specific to the element. Nebulizers. Nebulizers are also called atomizers. These are spray type in which stream of air passes over a capillary tube dipping into the test solution. A very tiny drop of test solution are produced which are then passed with the help of direct injection system along with the air stream into the burner for volatilization of atom. Various gases are mixed in air to produce flame. These mixtures of air and natural gas, air propane gas and air plus acetylene gas, which generates temperature from 1500 C to 2500 C. Monochromator and detectors. A simple filter, prism or grating monochromator are commonly used in AAS. Instruments with both single and double beams optics are used. Detectors are photocells. The reading in AAS is in visible range, i.e. extinction ranges from 0 to infinity. The desirable wavelength falls between 190 to 800 nm. Applications. Extensively used in biochemistry laboratory for studying body fluid composition. The composition of blood, urine, saliva, and cerebrospinal fluid can be assayed by AAS. Elements like Na, K, Ca, Mg levels are measured. Up to 1 to 3 ppm concentration. These are extensively used to study elements in plant after extraction from the plant sample. Atomic emission spectroscopy. Atomic emission spectroscopy (AES or ODS) uses quantitative measurement of the optical emission from excited atoms to determine analyte concentration. Analyte atoms in solution are aspirated into the excitation region where they are dissolved, vaporized, and atomized by flame, discharge, or plasma. These high temperature ionization sources provide sufficient energy to promote the atoms into high energy levels. The atoms decay back to lower levels by emitting light. Since the transitions are between distinct atomic energy levels, the emission lines in the spectra are narrow. The spectra of multi-elemental samples can be very congested, and spectral separation of nearby atomic transitions requires a high-resolution spectrometer. Since all atoms in a sample are excited simultaneously, they can be detected simultaneously, and is a major advantage of AES compared to atomic absorption spectroscopy. C7. Plasma emission spectroscopy. In plasma emission spectroscopy, the exciting medium agent is plasma. The term plasma in physics means a very hot, high-temperature ionized gas, sometimes described as the fourth state of matter, the other three being solid, liquid, and gas. In this method of sample analysis, a plasma source is a basic component. Plasma emission spectroscopy is similar to optical emission spectroscopy in principles but differs in mechanism. In OES, the sample excitation is done by electric arc or spark mechanism in a temperature range of 3,000 to 5,000 degrees Celsius. In PES, the temperature range is 7,000 to 9,000 OC. The sample solution or the analyte solution is applied to the plasma source by a nebulizer assembly. On reaching the high temperature 7,000 minus 9,000 deg Celsius plasma, the solution attains this high temperature and all types of molecular bonds break down. Free atoms or ions, electrically charged atoms, are produced, which emit their characteristic spectra. A monochromator assembly is in position after plasma source for isolation of the desired analyte line or spectrum. The plasma emission is captured inside the chamber through a special, flexible vacuum fiber optics cable, which is connected by flange with another fiber light guide outside the chamber. Note that, due to the use of these flexible vacuum fiber optics, the light emission can be observed also at different positions in front of the plasma. The intensity of an analyte line is directly proportional to the concentration of that particular analyte element being analyzed in the sample solution. The detector and readout assembly gives us the concentration of the particular element in the sample. Modern instruments being computer controlled, the analysis is very fast and needs little operator skill. Depending on the technique of production, plasma may be of three classes: viz., DC argon plasma, microwave plasma, and inductively coupled plasma (ICP). The ICP is the most widely used due to mechanical simplicity and operational advantages. Therefore, plasma emission spectroscopy is a method of analysis of various elements in a sample by passing the sample analyte solution through a plasma high-temperature ionized gas source, thereby exciting the outer orbital electrons of the analyte with simultaneous emission of electromagnetic radiations in the form of lights which are analyzed by means of a spectrograph, which separates various wavelengths of analytes in the sample. D1. Principal statistical methods in biological research. Nowadays in every sphere of human activities, statistics is used fruitfully and is necessary for effective decision-making in various fields of life. There is no doubt that statistics has become indispensable in all spheres of human life. Definition. The branch of science which deals with methods of collection, classification, analysis and drawing inferences from data, testing a hypothesis, making recommendations, etc., is called statistics. The term statistics has been derived from a Latin word, status, or an Italian word statista, which means political state. Statistics began in the distant past to collect facts about the state or the people who compose the state. For assessing the military potential, wealth, taxation rate, population growth and other aspects, kings and ruling chiefs needed key information regarding land, agriculture, commerce, population, etc. These pieces of information obtained in numerical form called data was collected for the purpose of the state, which came to be commonly known as statistics. Thus, statistics emerged into existence as the science of statecraft. Statistics has wide application in almost all sciences, social as well as physical such as biology, medicine, agriculture, veterinary, economics, psychology, business management, etc. It plays a major role in bioscience because data of bioscience are of a variable nature. The use of statistics in biology is known as biostatistics. It is concerned with the application of statistical data and statistical methods to solve problems of bioscience. Principle and practice of statistics in bioscience. In biological experiments, it is very difficult to draw a concrete conclusion because of inherent differences between two individuals. Homozygous twins are even not exactly alike in appearance, physiology, and behavior. While studying the effect of factors and natural differences between different individuals should be taken into account to arrive at a precise, meaningful interpretation. Various statistical analysis will be required to arrive at a definite conclusion. The results, therefore, have no meaning at all unless the data are analyzed to get a qualified numerical estimate. Most of the happenings in life science depends upon counting or measurements. Plants and animals obtained by any hybridization experiment agree with Mendel's law or not can only be concluded by statistical tests i.e. 2. High or low blood pressure has no meaning unless it is expressed in numbers. Blood pressure, pulse rate, HB%, rate of transpiration, action of a drug on an individual or group or any other measurement varies not only from person to person but also from group to group. The extent of this variability and characterized by way of chance, i.e. biological or normal, is learned by studying statistics as a science. Use of statistical methods are constantly increasing in biological sciences. The development of biological theories are closely associated with statistical methods. Heredity, one of the recent branches of biology, is mainly based on biostatistics. Therefore, for the students of life science, the knowledge of biostatistics is very essential. Statistical terms and symbols. Term is a word used to explain a particular identity. Symbol is a marker sign with a particular meaning. The use of terms and symbols allows statisticians to deal with general expressions and general results. By doing so, considerable saving in space and time takes place. 1. Population. Population may be defined as a group of organisms of one species occupying a definite area. In statistics, population is a well-defined group which is being studied. Suppose one has to study the incidence of bird flu infection in chicken. For this purpose, 100 chicken are collected randomly and brought in the laboratory. Here, 100 chickens are population for this experiment, and results will represent the universal population of chicken. In other words, in statistics, population always means the total number of individual observations from which inferences are to be made at a particular time. All fishes of one species in a pond or all plants of one species in a forest represent the population. Population may be finite or infinite. If a population consists of a fixed number of values, then it is said to be finite. For example, the number of earthworms in a piece of land, the number of patients in a hospital, the number of plants in a boundary, etc. On the other hand, population in which it is not possible to observe all the values of a variable, it is infinite. An infinite population is unlimited in size, e.g. the number of RBCs in human body, the number of zooplanktons in sea, and so on. 2. Sample. The selected part of a population is known as sample. In statistics, population always means the total number of individual observations from which inferences are to be made at a particular time. A sample represents a small collection of the population which has actually been observed. For example, all patients of AIDS of the world represents the population, whereas individual observations on 10 or 20 or 30 any convenient number of patients from the population refer to a sample. 3. Data. A set of values recorded for an event is called data. The data in statistics are generally based on individual observations. The HB% of 10 patients suffering from Kala-Azar was measured as 10.2, 9.6, 8.8, 10.7, 9.9, 10.8, 11.3, 9.5, 8.9, 8.8, mg 100 milliliters. Here 10.2, 9.6, 8.8 milligrams L00 ml are set of values for an event, i.e. HB% and is called data. 4. Observation. Measurement of an event is called observation. For instance, blood pressure, temperature of body, oxygen consumption, etc. are events, whereas 160 milliliters and 80 milliliters upper and lower pressure, 106 degrees Fahrenheit, 65 kilograms per hour, 100 milliliters are the respective observations. The source that gives observations such as object, person, etc. are called observational units. In biostatistics, the term individuals or subjects is used for observational units. 5. Parameter and statistic. A value calculated from a defined population such as mean, micropopulation, standard deviation, sigma, standard error of difference of mean sigma, 2 1x minus x, etc. are called a parameter. It is a constant value because it covers all members of the population. Familiar examples are mean height, birth rate, fecundity, and mortality rate, etc. of any one species of animals or plants. The quantity calculated to represent a character of population is known as parameter, whereas quantity calculated to present the character of the sample is called statistics. The former is a constant quantity, whereas the latter is variable. In other words, we can say that the numerical quantities which characterize a population in respect of any variable are called parameter. For example, if the variable is in length and the measurement of length is taken for the entire population, the mean length can be regarded as parameter, but the mean length of the sample can be regarded as statistic. Standard deviation of sample S and standard error of difference of mean S, 2 1x minus x of sample or statistic. In biological experiments, values calculated from a large sample is often applied to population and may be a valid estimate of population. Therefore, in biostatistics, though not desirable, parameter and statistic are often used as synonyms. 6. Variable. Any quantity or quality liable to show variation from one individual to the other in the same population is known as variable. An individual observation of any variable is known as variate. If we measure the height of some individuals of a population and obtain some values, the obtained values is variable. There are two types of variables. I quantitative and E qualitative. Quantitative variable is the one where the individuals are distinguished by measurement. Some examples of quantitative variables include the values of height, weight, length, HB%, oxygen consumption, etc. of individuals. In the case of qualitative characters, the individuals comprising the material under consideration are distinguished by some quality. White fur of rabbits, curly hair of sheep, wrinkled or smooth surface of seeds, different colors of flowers, etc. are instances of qualitative variables. A variable is a symbol such as x, y, z, etc. that may take any value in some specified set of numbers. Whatever the value of the variable actually observed is the actual value as denoted by the x1, x2, x3, xn or y1, y2, y3, yn or z1, z2, z3, cn. The possible values of a variable are those values that the variable may possibly take. For example, the weight of fish is in a pond may take any value between x1, x2, x3, xng. Both x1 and x2 are inclusive. Depending on the continuity or break, variables are of two types. A discrete variable is one which cannot take all the values and there is a gap between one value and the other. For example, the number of zooplanktons in 5 ponds were obtained is 98, 305, 387, 105 and 208. So in this case, number of zooplankton is a discrete variable. Number of persons in a family, no. A books in a library are discrete variable because they cannot take functional value. One cannot say that there are 3.5 persons in my family or there are 500.6 books in a library. The discrete variable may take any integer value from 0 to infinity. B continuous variable is the one which can take any values and there is no interval. For example, the weight and height of human beings is a continuous variable because it may take any value. Height of students in a class may be 120 centimeters, 120.2 centimeters, 120.5 centimeters, 120.7 centimeters, 120.9 centimeters, and so on. Measurement of HP%, CO2 consumption, etc. present continuous variable. Generally speaking, discrete variable take integer value while continuous variables take fractional values. 7. Functions of statistics. In statistics, statisticians are often interested in related variables. For example, a person's weight is related to his age, the weight of fish is related to its length, and so on. There is special relation between variables which characterize a function. The idea of a function is that as soon as we know the value of the first variable, the corresponding value of the second variable is also known. Consider the set of all possible ordered pairs of values of x with the corresponding values of y. This set is a function. We write y equals fx. The variable x is called the independent variable. The second variable y is called the dependent variable. Linear function. Consider, for example, the following relation between the demand and price of fish, d equals a plus bp. Such a relation is a functional relation involving some constant, e.g. and b, and the variable d and p here denotes the constant return in b, denotes the price elasticity of demand. If we consider the relation y equals a plus bx where y denotes the consumption and x denotes the income, then it denotes the constant return in b, denotes the marginal propensity to consume. In general, a linear function connecting y and x may be expressed as y equals a plus bx. One refers to this in equation of a straight line. The values of a and b are known as the coefficients of the equation and denote respectively the constant associated with the equation and the slope of the line. From this equation one may deduce the value of y for given values of x. For example, if y equals 3x4 then equals minus 4 and b equals 3 and for value of 6 of x, there corresponds to values of 14 of y. A linear equation is also used to express a functional relation like d equals fp, pl, p2 where more than one independent variables are involved. A suitable relation could be d equals a plus bp plus cpl plus cp2. The coefficients a, b, c, and d have similar interpretations as in case of d equals a plus bp. Nonlinear function. Equations where the power of x is more than 1 are called the nonlinear equations. An example of a nonlinear equation would be the quadratic equations y equals a plus bx plus cx2. In such circumstances, the marginal productivity of x is no longer simply the coefficient b, as in case of the linear function, but it also involves the coefficient c, so that no direct interpretation of the marginal productivity is possible. 8. Class interval. Each group into which a raw data is condensed is called a class interval. Each class is bounded by upper and lower figures called class limits. 9. Class size. The difference between the true upper limit and true lower limit of a class is called the size of the class interval. 10. Frequency distribution. The raw data are ungrouped data unless they are arranged in a systematic way, do not give any clear idea of the subject matter. Biostatisticians, therefore, arrange the raw data in ascending or descending order of their magnitudes. This arrangement is known as an array. Arrayed data is kept in such a manner that each variable exhibits its repetition number, i.e. frequency of variable. This is called frequency distribution. 11. Range. Range of the arrayed data is the difference between the maximum and minimum observation in a variable. 12. Cumulative frequency. The cumulative frequency corresponding to any value of the variable or a class is the sum of all the frequencies. D2 samples and populations. A group of organisms of one species, occupying a definite area is known population. But in statistics, population is a well-defined group which is being studied. A sample is a small collection of the population which has actually been observed. In biological experiment, it is rarely possible to collect complete information about a population. We cannot take out blood of whole body of all individuals of the population to know the HB% of RBC's count of human being, Homo sapiens. To ascertain RBC's count of HB% of human being, a few drops of blood of a few persons of different parts of the world was taken out and was observed microscopically by hemometer. Whatever is observed in a few drops of sample individuals is true for RBC's count of HB% in the blood of Homo sapiens. The data obtained from sample is computed and the result is obtained. From the above discussion, it is very clear that only few items are selected from the population in such a way that they represent the population. Such a section of the population is sampled and selection of a part of the population to represent the whole population is known as sampling. Every population consists of individuals or items which are known as sampling units. Sampling is a device which makes one to be able to draw inferences about the whole population simply by observing or measuring a few of the sampling units. Essentials of sampling. Selected samples from the population should be homogeneous and should not have any difference when compared with the population. Reasonable number of items is to be included in the sample to make the result more reliable. The selected sample should have similar characteristics as the original population from which it has been selected. The individual items composing the sample should be independent of each other. The number of observations included in a sample should be more to make the results more reliable. Size of the sample. The size of the sample plays an important role in life science. The size of the sample is the number of sampling units which are selected from a population for investigation. To get accurate results and for convenience in applying biostatistical methods, the size of the sample should be neither too big nor too small. It should be optimum. Methods of sampling. The proper methods of selection of samples and the relation between the sample and population is a matter of the theory of sampling. There are various methods of sampling. 1. Simple random sampling. A random sample is a sample where each item of the population has an equal chance of being included in the sample. In context of random sampling, random is not used in the sense of haphazard. Random sampling suggests that selection should be made without deliberate discrimination, but in practice it is very difficult if not impossible. For instance, determining the number of cell X and its dimension in a particular tissue, an experimenter might focus his microscope field to a particular area of the slide and get the mean number of the cell X. The result would be that the sample mean of X would tend to exceed the mean number of the actual mean of cell under study and the sample would be biased. To ensure randomness of selection, one can adopt either lottery method or refer to table of random numbers. 1. Lottery method. This is the simplest and most popular method of selecting a sample from a finite population. In this method, all items of population are numbered on separate slips of identical shape, size, and color. These slips are shuffled well and a blindfold selection is made. Suppose 10 patients are to be put on a trial out of the 100 available. Note the serial number of patients on 100 cards and shuffle them well. Draw out one and note the number. Replace the card drawn. Reshuffle and draw the second card. Repeat the process till 10 numbers are drawn. Reject the card that is drawn for second time. The 10 cards drawn thus will indicate the patient's number to be put on trial and the 10 patients selected in this manner form a random sample. Similar procedure is observed for selecting the control specimen. 2. Table of random number method. If the population size is very large, the application of the lottery method becomes difficult. Therefore, there is a tendency to use a table of random numbers for drawing the samples. One can use a table of random numbers from any position either horizontally or vertically. A suitable way to choose a starting point is to put a pencil blindly on some number and start reading from this point. For example, if we want to select 10 fishes from 200 fishes in an aquarium, each fish should be assigned a number from 001 to 200. In the 5-digit numbers of Snedeker and Cochrane 1988, we can take into consideration only the first 3 digits and the latter 2 are ignored. If we begin from 5 line and 39 column, the following numbers will have the first 3 digits less than 200. Begin from the number which falls in 5 line and 39 column, i.e. 20,002. The numbers coming after this are 05217, 03164, 19,774, 12,696, 05437, 17,805, 09609, 09284, 17,771. Thus the sample selected in this way will have the following numbers ignoring the last 2 digits: 200,052,031, 197, 126,054, 178,096,092, 177. 2. Systematic sampling. It is usually applied to field studies when the population is large, scattered and not homogeneous. Systematic procedure is followed to choose a sample by taking every kth individual where k refers to the sample interval, which is calculated by the formula k equals total population. Sample size desired, e.g. if 20% sample is to be taken out of 1,000 individuals. K equals 120th of a percent of 1,000 equals 5. One random number is found by pulling out one card after shuffling. Out of 10 cards, serially numbered 1 to 10. Supposing it is 7, then the sample will consist of units with sample number 7. 7 plus 10 equals 17. 17 plus 10 equals 27. 27 plus 10 equals 37, and so on. Examine every 10th individual after the 7th. This was done to assess incidence of influenza in one epidemic in a large city like Chennai. Merits of systematic sampling. 1. The systematic sampling is simple and convenient to adopt. 2. The time and labor involved in the collection of sample is relatively small. 3. If the population is infinite, homogeneous and each unit is numbered, then this method can give accurate result. 3. Stratified sampling. This method is followed when the population is not homogeneous. The population under study is first divided into homogeneous groups or classes called strata, and the sample is drawn from each stratum at random in proportion to its size. This method of sampling is for giving representation to all straight-up populations such as selecting sample from defined areas, classes, ages, sexes, etc. This technique gives more representative sample than simple random sampling in a given large population. For example, the entire human population may be divided into 5 socioeconomic groups. 10% may be selected for study out of larger groups and 50% or even more from smaller groups so that no subsample is less than 30 in size. Merits of stratified sampling. Proportionate representative sample from each group is secured and it gives greater accuracy. IV cluster sampling. A cluster is randomly selected group. This method is used when units of population or natural groups such as schools of fishes, hospital ward, slums of a town, etc. The technique of cluster sampling allows small number of the target population to be sampled while the data provided statistically valid at 95% confidence limits. As per module approved by WHO, it is most often used to evaluate vaccination. B. Non-random sampling. Non-random sampling methods are those which do not provide every item in the universe with a known chance of being included in the sample. The selection process is partially subjective. The choice of sample items depends exclusively on the judgment of the investigator. Hence, non-random sampling method is also called as judgment sampling. The investigator exercises his judgment in the choice and includes those items in the sample which he considers most typical of the universe with regard to the characteristics under investigation. For example, if sample of 200 fishes is to be selected from a pond of 1,000 fishes, for the study water percentage in a body, the investigator would select 200 fishes which will represent the population. Choice of sampling methods. The different methods discussed above can be used in different situations, wherever they are appropriate. However, it is difficult to say that a particular method would always be better than the rest. No one method can be regarded as the best under all circumstances. A number of factors such as the size of the sample, the size and nature of population, time, and finance for sampling, etc. would influence the selection of a particular method of sampling. The choice of sampling plan must be decided according to the different factors. D3. Measures of central tendency: average, mean, median, mode. Generally, it is found that values of the variable tend to concentrate around some central value of observations of an investigation, which can be taken as representative for the whole data. This tendency of the distribution is known as central tendency, and the measures devised to consider this tendency are known as measures of central tendency. One of the most important objectives of measures of central tendency is to get a single value that describes the characteristic of entire mass of statistical data. Such a value is popularly known as average. Measures of central tendency is a method of condensing a mass of data to a single value which is typical in representing the entire data. Types of measures of central tendency. There are usually 3 basic measures of central tendency. These are 1. Mathematical average. 2. Averages of position. 3. Measures of partition values. 1. Mathematical average. Averages represented purely in mathematical values are known as mathematical average. It is of 3 types: high arithmetic mean, e geometric mean, high harmonic mean. 2. Averages of position. Mean exhibited by position is called average of position. It is of 2 types: stat phase, height, median, and beat mode. 3. Measures of partition value. It is measures of location. It divides the total observations by an imaginary line into 2 or more parts expressed in percentage. 1. Mathematical average. High arithmetic mean. Central value or average, obtained arithmetically, is known as arithmetic mean. It is the most common average used in our day-to-day life. Depending upon whether all the items in the data are to be considered of equal or unequal importance, we get 3 subtypes of arithmetic mean. Accordingly, arithmetic mean is of following types: 1. Simple arithmetic mean. 2. Weighted arithmetic mean, and 3. Combined mean. 1. Simple arithmetic mean. It is most commonly used of all the averages. It is the value which we get by dividing the aggregate of various items of the same series by the total number of observations. Arithmetic mean ungrouped data. If the values of n items are x1, x2, x3, xn be the value of varied x, then simple arithmetic mean x is obtained by dividing the sum of the values of all the items by the total number of observations. Symbolically, x equals x1 plus x2 plus x3 plus xn of x equals sigma x. N arithmetic mean grouped data. A discrete series. If data is in frequency distribution but not in class interval, then it is called a discrete series. For computation of arithmetic mean in a discrete series, each value of the variable is multiplied by their respective frequencies. Sum of all values is obtained which is divided by total number of frequencies. Let the variable x take the values x1, x2, x3, xn and let their frequencies be f1, f2, f3, fn. Then the arithmetic mean x is computed by formula. X equals fx1 plus fx2 plus fx3 plus fxn of x equals sigma f, xnn. B. Continuous series. In the case of group continuous series, the arithmetic mean is calculated after taking into consideration the midpoints of various classes. Hence, formula given for discrete series is also applicable to group continuous series. X equals sigma f, m. N where x equals arithmetic mean. Sigma f, m equals sum of values of midpoints multiplied by their corresponding frequencies. Sigma f equals sum of frequencies. M equals midpoints of various class intervals. Midpoint m is obtained by following method: m equals lower limit of c plus upper limit of c2. Example: rate of restoration of 50 fishes of the species and the frequencies are given in continuous series. Find out mean of this experimental data. Rate of rest: 11011 2021 3031 40 4150 5160 6170 7180. Frequency: 3117410 573. Solution: make a table of 4 columns. First column for class interval of variable, second for midpoint, third for frequency, and fourth for mid-value multiplied by their respective frequencies. Class interval mid-value freak, mid-value x freak. CMFMXF 1 to 10, 1 plus 10, 2 equals 5.503, 5.5x 3 equals 16.5, 11 to 20, 11 plus 0.20, 2 equals 15.51, 15.5x 11 equals 170.5, 21 to 30, 21 plus 30, 2 equals 25.5, 7.5.5x 7 equals 178.5, 31 to 40, 31 plus 40, 2 equals 35.5, 35.5x 4 equals 142.0, 41 to 50, 41 plus 50, 2 equals 45.5, 145.5x 10 equals 455.0, 51 to 60, 51 plus 60, 2 equals 55.5, 55.5x 5 equals 217.5, 61 to 70, 61 plus 70, 2 equals 65.5, 7, 65.5x 7 equals 458.5, 71 to 80, 71 plus 80, 2 equals 75.5, 75.5x 3 equals 226.5. Sigma f equals 50 sigma f, m equals 1925 x equals sigma f, m n equals 1925 50 x equals 38.5 ans. 2. Weighted arithmetic mean. One of the limitations of the arithmetic mean discussed above is that it gives equal importance to all the items. But there are numerous instances where all the items do not have the same degree of importance. When this is so, we compute weighted arithmetic mean. The term weight stands for the relative importance of the different event items. For example, if the length of various rare species of plants in a forest is given, numbering is according to rarest to rare, and the average length of a species is to be calculated, then if the length of all the species are given the same importance and a simple average of the length is obtained, it will not truly represent the length of an average species. The length of 6 species of rare plants, rarest to rare, is given below. SP 1 SP 2 SP 3 SP 4 SP 5 SP 6 1500 1700 500 200 100. The simple average equals sigma x n equals 4006 equals 666.6 centimeters. This average length is much above the length of SP 4 SP 5 and SP 6. Hence there arises the need to assign weights to the values of multiplying factors proportional to its importance to each item of the data and to calculate a weighted arithmetic mean. The weighted arithmetic mean is the sum of the products of the values with their respective weights divided by the sum of the weights. Thus, let W1, W2, W3, Wn be the weights of the values xl, x2, x3, xn respectively. Then the weighted arithmetic mean xw is given by x equals w1 x1 plus w2 x2 plus w3 x3 plus wn xn of x equals sigma wi, xnn. 3. Combined mean. If x1 and x2 are the arithmetic mean of two series whose number of terms are n1 and n2 respectively, then the combined mean x is given by x equals n1 x1 plus n2 x2. N. 2. Geometric mean. The geometric mean of a set of n positive values is defined as a positive nth root of the product. Computation of geometric mean for ungrouped data individual series. If x1, x2, x3, xn are the numbers of the data, then their geometric mean g equals n. x1, x2, x3. xn equals x1, x2, x3, xn l n where x1, x2, x3, xn are the n values of varied x. This can be written as equals n area summation equals n I n g nt 1 log 1 log. Note: in practice, the computation of the nth root of the product of n item value is very difficult, and as such logarithms are used to facilitate the computation of geometric mean. For this reason, geometric mean is also referred as logarithmic mean. When logarithms are used, geometric mean g can be calculated as the arithmetic mean. The logarithm of g is equal to the arithmetic mean of logarithms of individual values. This can also be written as equals n area summation equals n I x n g anti 1 log 1 log 3 harmonic mean. If variables are expressed in ratios or rates, the proper average to be used is the harmonic mean. The harmonic mean is defined as a reciprocal of the arithmetic mean of the reciprocal of the given values. For example, reciprocal of 5 is 1/5, reciprocal of 9 is 1/9, and so on. It is applicable only in a restricted field such as oxygen consumption H, pulse rate per minute, calorie requirement of a child per day, etc. Computation of harmonic mean for ungrouped data. N area summation equals equals 1/1/1 x n x n hem 2 averages of position. As the name suggests, averages of position indicate the position of an average in a series of observation arranged in increasing order of magnitude. Averages of position is of two types. Median. A median of a distribution is defined as the value of that variable which divides the total frequency into two equal parts when the series is arranged in ascending or descending order of magnitude. A median for ungrouped data. Median value is the value of the n plus 1/2 th item. Median is computed differently if number of observation n is odd and when even. In case of even series computation, a median is slightly different than odd series. Median is given by arithmetic mean of the two middle terms, n2 th and n plus 1/2 th item. Be continuous series. In this case, the median cannot be found directly without recourse to the original data. It may, however, be estimated with sufficient accuracy by interpolation. To do this, we first find the position of the median item, i.e., n plus 1/2, and from the cumulative frequencies of the class, we determine the class in which the median item occupying this position lies. Then the median is obtained by the formula x f n c median l m minus equals plus 2 1 h, where L1 equals lower limit of the class in which median lies. Fm equals frequency of the class in which the median lies. C equals cumulative frequency of the class preceding the median class. N equals total frequency and H equals width of the class interval of the median class. 2 mode of frequency distribution is defined as that value of the variable for which the frequency is maximum. The definition of mode indicates that mode cannot be determined from a series of individual observations. It depends on the frequency of occurrence of the items. Hence, to get the value of mode, the series must be converted into a frequency distribution. In discrete series, if the distribution is regular and only one maximum frequency is if data is unimodal, then the mode value can be obtained by near inspection. Sometimes the series have more than one mode, bimodal or multimodal. Then mode is obtained by grouping method. D4. Statistics of dispersion, mean deviation, standard deviation, and variance. In statistics, dispersion is used commonly to mean scatter, deviation, fluctuation, spread, or variability of data. Dispersion is used to denote a lack of uniformity in item values of a given variable. The degree to which the individual values of the variance scatter away from the average or the central value is called the dispersion. The measure of variation is one of the important tools of statistics for biologists because biological phenomena are more variable than that of physical and chemical sciences. Length, weight, HG%, RBC's number, rate of oxygen consumption, etc. Two individuals of same species, of same age and sex will differ definitely. Same plant of sweet pea produces different number of seeds in different pods. Same person exhibits different pulse rate and heartbeat in different physiological conditions. Cure rate with the same drug varies in different patients, even of same age and sex. There are 5 different measures of variation. 1. Range. 2. Semi-interquartile range or quartile deviation. 3. Mean deviation. 4. Standard deviation. 5. Variance. 1. Range. Range of the raw data is the difference between the maximum and minimum observations in the data. Range equals HL. Here R equals range. H equals highest value of variable. L equals lowest value of variable. Coefficient of range. The coefficient of the range or the relative measure of the range is obtained by applying the following formula. Coefficient of range equals LS difference of extreme items L plus S sum of extreme items. 2. Quartile deviation. The half distance between 75th percentile i.e., third quartile Q3 and 25th percentile i.e., first quartile Q1 is called quartile deviation or semi-interquartile range. In normal distribution, semi-interquartile range is called probable error PD. Q is one half the range of the middle, 50% cases in a distribution. Fig. Showing first quartile Q1 median Q2 and third quartile Q3. Figure shows that Q1, Q2, and Q3 divide the range of the variable into 4 parts. Q1 divides the range of the variable into 25% and 75% observation. Q2 divides the range of the variable into 50% and 50% observations, and Q3 divides the range of variable into 75% and 25% observations. Formula. Q equals Q3 Q2 plus Q2 Q1 equals Q3 Q1. 2 to the semi-interquartile range takes into account only the middle half of the data between Q3 and Q1. If Q is larger, there is greater scatter in the interquartile range. If Q is smaller, there is greater concentration in the middle. If the distribution is symmetrical, Q3 Q2 equals Q2 Q1, 25% of the observations above and below lie equidistant from the median. Coefficient of quartile deviation. It is calculated by this formula. Coefficient of Q equals Q3 Q1, Q3 plus Q1. Merits of quartile deviation. The quartile deviation is a better measure of dispersion as it is not based on two extreme values like range, but rather on middle 50% observations. It is the only measure of dispersion which can be used for open-end distribution. 3. Mean deviation, average deviation. The mean deviation is the average of the absolute values of the deviation from the mean or median or mode. Let us understand the fact that each variable in any distribution deviates from the mean. The scatter above or below the mean, unless it happens to coincide with the mean where deviation is 0, is regarded as deviation. Deviations above the mean are negative deviation and below the mean are positive deviation. Computation of mean deviation denoted as delta, ungrouped data, individual series. Mean deviation or MD or delta equals n x n area summation for ungrouped data. Here, MD or delta equals mean deviation. X equals deviation from actual mean, sigma x equals sum of all deviations of a distribution. II equals not considering sign plus failure A while summation is done. Following formula is applied to obtain deviation, i.e. deviation equals square mean or x equals xx. Note, x is used for square variable whereas x is used for deviation and x is used for mean. B. Computation of mean deviation for group data, continuous series. In this case, the same above formula as in the case of discrete series is applied when midpoints of each class interval is obtained. Delta equals n area summation. N area summation. F. F. X coefficient of mean deviation. Coefficient of mean deviation denoted by C of delta x is obtained by formula. C of delta x equals delta x. X merits and demerits of mean deviation. Mean deviation is easy to calculate, but since mean deviation has less mathematical value, it is rarely applied for biological statistical analysis. It is also not meaningful because negative sign of deviations is ignored. 4. Standard deviation. Standard deviation may be defined as the square root of the arithmetic mean of the squares of deviations from the arithmetic mean. Computation of standard deviation as sigma for ungrouped data. Following 6 steps are observed before the computation of standard deviation. I calculate the mean. B. Find the difference of each variable from the mean. B. Square the differences of observations from the mean. IB. Add the squared values to get the sum of squares. B. Divide the sum by the number of observations minus 1 to get mean. Square deviation called variance. B. Find the square root of this variance to get root mean square deviation called standard deviation. Having squared the original, reverse the step of taking square root. Apply following formula to calculate standard deviation. N. X to n area summation sigma equals r. 1. 2. Minus equals n area summation. N. X. Sigma. Sigma. Where s equals standard deviation, x equals deviation obtained from mean, i.e. xx. N equals total number of observations. Note, s is computed by using n1 in the denominator of above formula instead of n as the size of sample, i.e. total number of observations is less than 30. If the size of sample is more than 30, then first mention formula. Computation of standard deviation for group data, discrete and continuous series. N area summation. N area summation equals f. Fx2. Sigma or n area summation. N area summation. Minus. Equals. 1. 2. F. Fx. Sigma. Merits. Standard deviation summarizes the deviation of a large distribution from mean in one figure uses a unit of variation. It indicates whether the variation of difference of an individual from the mean is real or by chance. Standard deviation helps in finding the suitable size of sample for valid conclusions and helps in calculating the standard error. Demerits. Standard deviation gives weightage to only extreme values. The process of squaring deviations and then taking square root involves lengthy calculations. Differences between mean deviation delta and standard deviation sigma. One, algebraic signs are ignored while calculating the mean deviation, but they are taken into account while calculating the standard deviation. Two, mean deviation can be computed either from the mean or median, but the standard deviation is always computed from the arithmetic mean, because the sum of the squares of the deviations of items from the arithmetic mean is the least. 5. Variance. Variance of a distribution is defined as the square of the standard deviation. Thus variance v equals sigma 2. Interpretations of variance. Suppose that we have a sample of only one case, with only one score. There is no possible basis for individual differences in such a sample, and therefore there is no variance or variability. Consider a second individual with his score in the same test or experiment. We now have one difference. Consider a third case and we then have two additional differences, three altogether. There are as many differences as there are possible pairs of individuals. We could compute all these interpair differences and could average them to get a single representative value. We could also square them and then average them. It is most easy to find the mean of all scores and to use that value as a common reference point. Each difference then becomes a deviation from that reference point, and there are only as many deviations as there are individuals. Even the variance of the SC is a single representative value for all the individual differences when taken from a common reference point. Worked example. Hemoglobin content in G 100 milliliters of 10 persons of locality was recorded as 7, 8, 9, 10, 11, 12, 13, 14, 15, and 15.5. Find out the variance of the data. Variance of sigma 2 equals 2, 2, 2, 2. Equals minus n area summation. N area summation x. F. Fx. Sigma. Variance is useful in ecological investigations including nutrition, reproduction, and behavior since it gives an indication how organisms are dispersed within the population. Population dispersion equals variance equals S2 mean x. Solution. Following table is prepared to calculate variance using formula. V equals sigma x2 n. Sigma x equals 115 and x equals 115 tenths equals 11.5. Sigma x2 equals 80.75 variance equals sigma x2 n equals 80.75 10 equals 8.075 answer. Coefficient of variance. The standard deviation S is an absolute measure of dispersion. The corresponding relative measure is known as the coefficient of variance. It is used in such problems where we want to compare the variability of two or more than two series. If, for an example, an analysis of seed number per fruit in two batches of 10 fruits in a garden, batch I has a mean score x1 equals 70 with SD S1 equals 1.25 and batch 2 has a mean score x2 equals 80 with SD S2 equals 2.4, then it is clear that batch having a lesser value of SDS are more consistent in producing seeds than the batch 2. We also meet situations when two or more distributions having unequal means or different units of measurements are to be compared in respect of their variability. For making such comparisons, we use a method of statistics called coefficient of variation. Coefficient of variation is denoted by CD and is calculated as CD equals SXX100. Example: following are the weights of two rats in 10 months. Both were fed same normal diet. If the consistency performance is the criterion, calculate which one maintains consistency. Solution: frame a table of 8 columns to obtain various values to calculate CD. Conclusion: since coefficient of variation is less 8.71 in the case of y rat as compared to x rat 9.44, therefore y is more consistent. D5. Test of statistical significance. Standard error. Confidence limits. Chi-square. In biological research, often we are interested in comparing a characteristic mean and variance of two samples. For example, we may prefer to compare the mean protein content of two varieties of chicken, mean 80% of men and women, yield of crop of two varieties, etc. A process to assess the significance of this difference is known as the test of significance. This test helps us in determining whether observed differences between two samples are actually due to chance or whether they are really significant. Procedure for carrying out a significance test. Laying down a hypothesis. In biological science, statistical tests of hypothesis play an important role. When population mean micro is compared with a sample mean x, the common way of starting the hypothesis is that there is no difference in between two mean values. In case of no difference or very small difference, our hypothesized value is correct. For example, in the case of childbirth, the assumption is that there is an equal chance of male and female birth. It asserts that there is no difference between the sample and population in the particular study under consideration. On the other hand, if the statistical test shows that the difference is significant, the hypothesis is rejected. Generally, two hypotheses must be considered. If one hypothesis is accepted, the other is rejected. The two hypotheses in a statistical test are normally referred to as one null hypothesis and two alternative hypothesis. 1. Null hypothesis. According to R. A. Fisher, null hypothesis HO is a hypothesis which is a test for possible rejection under the assumption that it is true. The null hypothesis is a very useful tool to test the significance of difference. In the process of statistical test, the hypothesis is accepted or rejected based on samples drawn from the population. Null hypothesis reveals that the mean of the sample and the mean of the population under study do not show any difference. A statistical hypothesis is a null hypothesis if it is accepted. One should take into consideration the following while dealing with null hypothesis. I to test the significance of the difference between the values of the sample and the population, or between two sample values, we set up the null hypothesis that the difference is not significant. This is so because the difference is due to sample fluctuations. HO, micro equals x where micro equals population mean and x equals sample mean. D to test any statement about the population, we set up the null hypothesis that it is true. 2. Alternative hypothesis. Any hypothesis which is complementary to the null hypothesis is called alternative hypothesis. Rejection of null hypothesis HO leads to the acceptance of alternative hypothesis which is denoted by each one. Suppose we want to test the null hypothesis for an average length of Indian earthworm, Veratinopostima, in a plot of 51 centimeters free. Now these two hypotheses can be represented as follows. HO, micro equals 51, null hypothesis. H1, micro equals 51 i.e. micro greater than 51 or micro less than 51, alternative hypothesis. Suppose we are interested in knowing the mean lifespan of human beings. All human beings will not have the same lifespan. The average lifespan will have to be considered. Let this average lifespan be micro years. Now, we may consider the following alternative hypothesis. I micro greater than 100 years, e micro less than 100 years, e micro equals 100 years. The test of a statistical hypothesis is based on a sampling distribution of some statistic calculated from a random sample from the population. The sampling distribution of the mean depends on the mean of the population from which the sample is drawn. The first two of the above three hypotheses do not specify precisely the mean of the population and hence the sampling distribution of the sample mean cannot be determined. Such hypothesis cannot therefore be considered. The hypothesis to be tested must precisely specify the mean of the population. Hence, only the third hypothesis e.g. micro equals 100 years can be considered. On the basis of above mentioned hypothesis, we can determine the sampling distribution of the sample mean and hence find out the probability of the observed sample value or more extreme values. If this probability is small, the hypothesis is rejected, otherwise accepted. No one can prove the hypothesis to be true. We can reject or accept it until fresh evidence against it is obtained. This is a peculiar characteristic of statistical hypothesis. We cannot prove it to be absolute by true. If it is near the truth, we accept it, but if it is a weight limit defined by error from truth, we reject it. A statistical hypothesis must be disprobable. Such hypotheses are called null hypotheses. Two types of errors in testing a hypothesis. The decision to accept or reject the null hypothesis HO is based on a sample study. There is always a chance of committing an error. However, there are two possible types of errors in the test of a hypothesis. 1. Type 1 error, rejection of null hypothesis which is true. 2. Type 2 error, acceptance of null hypothesis which is false. Following examples will make the distinction between the two types of errors more clear. Suppose the difference between two population means is 0, and if our test of significance indicates rejection of the null hypothesis, we commit type 1 error. On the other hand, if there is true difference between the two population means, our test of significance suggests acceptance of null hypothesis, then we commit type 2 error. Table gives an idea about the type 1 and type 2 errors. Reject H0, accept H0, H0 is true type 1 error, correct decision H0 is false, correct decision type 2 error. Table can be expressed as follows. 1. Rejects HO when it is true, type 1 error equals alpha 2, accept H0 when it is false, type 2 error equals beta 3, accept H0 when it is true, correct decision 4, reject H0 when it is false, correct decision. While testing hypothesis, we would like to minimize both the errors. However, due to the fixed sample size, it is not possible to control both the errors simultaneously. Researcher will be interested in deciding whether to accept or reject a null hypothesis. We always desire to minimize the chance of committing type 1 error alpha, then the chance of committing type 2 error beta we increase. In general, it is more risky to accept a false hypothesis type 2 error than to reject a true hypothesis type 1 error. Level of significance. The statistical test fixes the probability of committing type 1 error at a certain level, called the level of significance, and minimize the chances of committing the type 2 error. The level of significance is thus. The probability of committing type 1 error is usually denoted by alpha. The level of significance is usually chosen as 0.05% level of significance or 0.01 1% level of significance. 0.01 is used for high precision and alpha equals 0.05 for moderate precision. In most biometric tests, the level of significance is generally fixed at 5%. This means that the probability of accepting a true hypothesis is 95%. The problem before a researcher will be the choice of the level of significance. The choice of alpha is basically governed by the consequences of the two types of errors. These two types of errors can be easily understood with an example where a patient is given a drug to cure some disease. Type 1 error is when the drug has a positive effect, but it is considered that it has no effect or an adverse effect. Type 2 error, the drug has an adverse effect, but it is considered that it had positive effect. If the type 1 error is committed, the patient will be given another drug which may or may not be effective. On the other hand, if type 2 error is committed, the drug is continued in spite of an adverse effect. The patient is likely to develop some other complication or may even die. This indicates that the type 2 error is more severe than the type 1 error. Therefore, while drawing inferences about the null hypothesis, type 2 error minimizes even at a certain risk of type 1 error. 1 and 2 tailed tests of hypothesis. A sample statistic is used to test the hypothesis HO. In a test, the area under the probability curve is divided into two: regency acceptance region and the rejection or critical region. Significance of difference in means. Tests for significance of difference in means are discussed under two heads. 1 Z test for large samples. 2 T test for small samples applied as unpaired, two independent samples, and paired single sample correlated observations test. For application of either of the two tests C or T, standard error mean, i.e., a unit that measures chance variation has to be understood. Standard error mean. The quantity calculated to represent a character of population is known as parameter, whereas the calculated value presenting the character of the sample is known as statistics. The former is constant quality while the latter is variate. This property of statistics explains that when several samples are taken from population, their mean and standard deviation will vary from the parameter of the population. The difference of mean and standard deviation of samples from the parameter of the population is known as sample error. Computation of standard error mean SEX. Standard error means of samples drawn from a particular population could be calculated if means a large number of samples were known. To calculate the SEX, find the mean micro of the sample means X and then the differences of individual means from this grand mean X micro. Standard deviation of a series of means. For standard error mean equals 1, 2, minus n area summation n X micro. SEX for individual series. In practice, usually only one large sample is drawn and its standard error mean is calculated by the following formula. SE n 4 n STX sigma equals. Thus SEX is the SE of the sample divided by the square root of the number of observations in the sample. Signification test. If the observed difference between the two means is greater than 1.96 times the SE x1 x2, it is significant at 5% level of significance. The difference is unusual and may be due to influence of some external factor. If the observed difference is greater than 3 times the SE, it is real variability in more than 99% cases, and biological or due to chances in less than 1% cases. Standard error mean for group data. 1. Discrete series. Following steps have to be followed to obtain SEX group data. Find standard deviation applying following formula. N area summation. N area summation equals F Fx2 sigma if observation are more than 34. N area summation. N area summation minus equals 1, 2, F Fx sigma if observation are less than 30. Compute the value of SE and frequency F applying following formula to get SEM. SE N area summation equals F 4 F SDX sigma 3. Continuous series. Calculation of SEM in continuous series is just like discrete series. Here we have to obtain the value of each class interval and then proceed in same above given manner. Standard error of a standard deviation. Like mean, standard deviation also varies when obtained from different individuals of the same population. Hence, one can test the significance of standard deviation by standard error. Computation of SE of standard deviation for individual data. SE sigma n 4 n SD 2 2 sigma equals. SE sigma for group data discrete series. Following formula is applied to obtain SE of SD in discrete series. SE sigma equals n area summation equals F SD 2 Z test. To test the significance of difference between two sample means or between experiment sample mean and a control sample mean. Z equals observed difference between two sample means. SE difference between two sample means. Z equals x1 x2. Sigma x1 x standard error of difference is denoted as x1 x2 or sigma x1 x2. It is computed by formula. Sigma x1 x2 equals 2 2 2 1 2 1 n n sigma sigma plus. This formula is applied when micro and sigma of population are not known but the sample are large. Students T test. In biological experiments, it becomes essential to compare the means of two samples to draw a conclusion. Often we come across many instances of comparison between mean value of T4 injection and rate of respiration of two groups of species of animal, effective pesticide and control of insect. Such examples in biological studies need some statistical treatment before interpreting the results. In other words, visual expression of the difference between the two sample means usually fail to give significant difference. Therefore, the degree of level of significance of difference between two means is to be qualified to reach a definite conclusion. To test the significance of difference of means of two samples, W.S. Gossett 1908 applied a statistical tool called T test. The pen name of Mr. Gossett was student, and hence this test is called the student's T test. Student's T test is also known as T ratio because it is a ratio of difference between two means. Later on, Aylmer Fisher 1890-1962 developed student's T test and explained it in various ways. In student's T test, we make a choice between two alternatives. I to accept the null hypothesis, no difference between the two means. E to reject the null hypothesis, i.e. the difference between the means of the two samples is statistically significant. Determination of significance. Probability of occurrence of any calculated value of T is determined by comparing it with the value given in the T table corresponding to the combined degree of freedom derived from the number of observations in the samples under study. If the calculated value of T exceeds the value given at P equals 0.055% level in the table, it is said to be significant. If the calculated value of T is less than the value given in T table, it is not significant. Degree of freedom. The quantity in the denominator which is one less than the independent number of observations in a sample is called degree of freedom. In unpaired, T test DF equals n1. In paired T test DF equals n1 plus n2 to 2. n1 and n2 are the number of observations in each of the two series. Unpaired T test. This test is applied to unpaired data of independent observations made individuals of two different or separate groups or samples drawn from two populations. Following steps are taken to test the significance of difference. 1. Find the observed difference between means of two samples x1 x2. 2. Find the SE of difference between means of SED equals sigma x1 x2 equals 2 2 2 1 2 1 n n sigma sigma plus. 3. Now apply formula T equals x1 x2 2 2 2 1 2 1 n n sigma sigma plus. Pair T test. It is applied to paired data of independent observation from one sample only when each individual gives a pair of observations. Such situations are commonly faced in biological, agriculture, veterinary, and medical sciences such as 1. To study the role of a factor drug, pesticide, fertilizer, etc. when the observations are made before and after display EG of meals on glucose level in blood, effective drug on blood pressure, exertion, on pulse rate, a garlic pearl tablet on cholesterol levels in the blood. 2. To compare the effect of two factors, two drugs, two doses of pesticide or hormones, etc. given to same individuals in a sample at two different occasions, e.g., adrenaline, noradrenaline on pulse rate, number of hours for which sleep is induced by two hypnotides, and so on. 3. To compare results of two different techniques, e.g., estimation of HP% by Solis and Tallquist methods, microarray infection rate by fixed near and concentration techniques, examination of stools for hookworm mobilizing flotation and concentration F cubes, and so on. 4. To compare observations made at two different sites in the same body, e.g., compare temperature between mouth and rectum, mouth and sidearm of the same individual. 5. To study the comparative accuracy of two different instruments, e.g., two types of sphygmomanometers, hemometers, durometer, etc. In the case of unpaired T, test there are two samples similar in all respects to eliminate bias, which is often difficult. So pairing is a good idea when the results fall into pairs. One essentially starts with a null hypothesis. It is assumed that there is no real difference between the means of before and after observations. For testing the significance of difference. 1. Find the difference in each set of paired observations before and after x1, x2 equals x. 2. Calculate the mean of the difference x. 3. Compute the SD of difference and then the SE of mean from the same. N. SD. 4. Determine t value by substituting the above values in the formula. T equals xo equals x. N. SD SED. As for null hypothesis, there should be no real difference in means of two sets of observations, i.e., theoretically it should be 0. 1. Find the degree of freedom. Being 1 in the same sample, it should be n1 degree of freedom. 2. If the p is more than 0.05, the difference observed has no significance because such a difference can occur commonly due to chance. Thus, the factor under study may have no influence on the variable. But if p is less than 0.05, the difference observed is significant because such a difference is less likely to occur due to chance influence of the factor to which the sample is based may be accepted as an alternative to null hypothesis. D6. The chi-square test. Various tests of significance, such as C and T, tests discussed in the preceding chapter are parametric tests and apply to only quantitative data like length, weight, height, HV%, CO2 consumption, number of seeds per pod, etc. These tests were based on the assumption that samples were drawn from the normally distributed populations. There are many situations in which it is not possible to make any dependable assumption about the distribution from which samples have been drawn. In biological experiments, we also get qualitative data like the color, health, intelligence, pure response of drug, etc., in which observations are classified in a particular category, class, or group. For these qualitative data, non-parametric chi-square test is commonly used. In many studies, especially genetical studies, it becomes necessary to test the significance of overall deviation between the observed and expected frequencies. Chi-square test was developed by Professor A. R. Fisher in 1870. Carl Pearson improved Fisher's chi-square test in its known form in the year 1900. Chi-square is derived from the Greek letter chi and pronounced as here, ksy without s. Chi-square test is a test of significance of overall deviation squared in the observed and expected frequencies divided by expected frequencies. I formula for determining chi2, the chi-square chi2. Statistics is solved as follows: chi2 equals n area summation minus e o e2. Here, O equals observed frequency in a class, E equals expected frequency in a class. Sigma equals summation. From these equations, the value of chi2 will be 0 if O equals E in each classes, but due to chance error this never happens and the observed results are based on the number of degree of freedom df and the critical level of probability 5% or 1%. We can find the expected value chi2 from the table. This expected value can be compared with the value calculated from the data. If the tabular value is lower than the calculated value, then the results are significant. Common application of chi2 test. 1. As an alternative test to find significance of difference in two or more than two proportions, chi-square test is a very useful test which can be applied to find significance in the same type of data with advantages mentioned below, to compare the values of two binomial samples even if they are small. For example, while finding significance of difference in rate of respiration in 5 control and 5 thyroxine T4 treated animal of same species, significance of difference in yield of fruit and control in insecticide spray garden, etc. B. To compare the frequencies of two multinomial samples. Chi-square measures the probability of association between two discrete attributes. Two events can be studied for their associations such as iron intake and HV%, season and fecundity, T4 injection and oxygen consumption, nutrition and intelligence, weight and diabetes, etc. There are two possibilities: either they influence or they do not. 2. As a test of association between two events in binomial or multinomial samples. Chi-square measures the difference between two or more events. The chi2 test can be applied to find association between two attributes when there are more than find association between two discrete groups as happens in multinomial samples, i.e. to test the association between quantity of T4 injection 1 mg, 2 mg, 3 mg, 4 mg, 5 mg and rate of oxygen consumption, atmospheric temperature variations and water percentage of body, incidence of filiariasis and social classes, state of nutrition and intelligence quotient. Table is prepared by enumeration of qualitative data. Since one wants to know the association between two sets of events, the table is also called association table. 3. As a test of goodness of fit, chi2 test is also applied as a test of goodness of fit. Goodness of fit reveals the closeness of observed frequency with those of the expected. Thus it helps to answer whether something physical or chemical factors did or did not have an effect. If observed and expected frequencies are in agreement with each other, then the chi-square should be 0. Null hypothesis HO, but it does not happen in life science. There is always some degree of deviation. Prerequisites of chi2 test. There are 3 basic prerequisites of chi2 test such as: I sample must be random. The data should be qualitative. The preferably observed frequency should not be less than 5. Determination of the value of chi2. Following steps are required to calculate the value of chi2. 1. Make a contingency table and note the observed frequency 0 in each class of one event, row wise i.e. horizontally, and then the numbers in each group of the other event, column wise i.e. vertically. 2. Calculate the expected frequencies E. 3. Find the difference between the observed and expected frequency in each cell OE. If the deviation is large, the square deviation OE2 must be large. 4. Calculate the chi2 value applying formula. Chi2 equals n area summation minus E OE2. This will be the value of chi2 which ranges from 0 to infinity. 5. The calculated value of chi2 is compared with the table value with the given degrees of freedom either 5% or I% level of significance. If the calculated value of chi2 is less than the tabulated value at a particular level of significance, the difference between the observed and the expected frequencies is not significant and can have arisen due to fluctuations of sampling. On the other hand, when the calculated value is more than the tabulated value, the difference between the observed and the expected values is significant. Degrees of freedom df in chi2 test. While comparing the calculated value of chi2 with the tabulated value, we have to calculate the degree of freedom. The degree of freedom are calculated from the number of classes. Therefore, the number of degrees of freedom in a chi2 test is equal to the number of classes minus 1. If there are 2 classes, 3 classes, and 4 classes, the degree of freedom would be 2 to 1, 3 to 1, and 4 to 1, respectively. In a contingency table, the degree of freedom are calculated in a different manner. df equals r1 c1 where r equals number of rows in a table. C equals number of columns in a table. Thus in a 2x2 contingency table, the degree of freedom is 2 to 1, 2 to 1 equals 1. Similarly, in a 3x3 contingency table, the number of degree of freedom is 3 to 1, 3 to 1 equals 4. Likewise, in 3x4 contingency table, the degree of freedom is 3 to 1, 4 to 1 equals 6, and so on. Contingency table. We have already discussed above that the value of chi2 depends on number of classes, or in other words, on the number of degrees of freedom dt and the critical level of probability. Association attributes can be shown by the table called contingency table. D7. Probability distributions normal, binomial, and Poisson. Observed frequency distribution, which are results of actual observations, have already been discussed. But sometimes the knowledge of distribution, which are not based on real observations, become essential. One can mathematically reduce frequency distribution of hypothetical values. In a series, values of a random variable is known as theoretical probability distribution. Theoretical probability distribution is of 3 types. 1. Normal distributions. 2. Binomial distribution. 3. Poisson distribution. 1. Normal distribution. In a population, many characteristics show a complete gradation without any break from one extreme to the other. This is signified most closely by characteristics such as mass, linear dimension, shape, and color of organisms. If measures of distribution are arranged in linear fashion and vary continuously on both the sides from the central value, then the distribution is called normal distribution. In normal distribution, measures are concentrated closely around the center and taper off from the central high point to the left and right. There are relatively few measures of the low score, end of the scale, an increasing number up to a maximum at the middle position, and a progressive falling off towards the high score, end of the scale. The normal distribution is concerned with all numbers whether complete or in a fraction. For example, if we study the height of Americans, the height of most of the Americans will be between 162 to 192 centimeters. Height of very few Americans will be between 152 to 167 centimeters, lower end of the scale, and between 282 to 215 centimeters, higher end of the scale. One can understand it more clearly by drawing a graph representing variables on horizontal line and frequencies on vertical line for frequency distribution. Let us plot a graph for the body weight in g and the frequencies of 149 fishes given below. Normal distribution curve. The curve plotted with the help of data of normal distribution presents a bell-shaped symmetrical curve called normal distribution curve. This curve is also known as the Gaussian curve. The Gaussian curve is continuous for continuous variables. It shows that the mean value of the variable lie at the peak of the curve and the largest number of observations lie at this point. As the ordinate divides the area under the normal curve into 2 equal parts, the median of distribution coincides with the mean. The points of inflection of the normal curve are equidistant from the mean. The variance of variables having lower values lie on the left side of the mean, while variance having higher values lie at the right side of the mean on horizontal line. Relationship between normal curve area and standard deviation. Figures bear 3 uprights at the points corresponding to 1, 2, and 3 times the standard deviation of the variables on each side of the mean. The fig shows following features. 1. The first and third quartiles are equidistant from the median at a distance of 0.6745 sigma. Thus, the semi-interquartile range is equal to 0.6745 of the standard deviation. 2 mean plus or minus 1 sigma covers 68.27% area, i.e. relative frequency. This suggests that in a normal distribution, 68.27% of the observations lie within a distance equal to the standard deviation on each side of the mean, i.e. 34.135% area will lie on either side of the mean. 3 mean plus or minus 2 sigma covers 95.45% area, i.e. relative frequency. 4 mean plus or minus 3 sigma covers 99.73% area, i.e. relative frequency. It covers almost entire area of the curve. Only 0.27% area remains outside the curve. 5.50% of observations lie in an area bounded by a distance of 0.6745 sigma on each side of the mean, shown as dotted line in figure 7.2. Besides above points, following facts are also considerable in context of curve area. X plus or minus 1.963 sigma covers 95% area. X plus or minus 2.57 sigma covers 99% area. X plus or minus 0.6745 sigma covers 50% area. Properties of normal distribution curve. 1. Normal distribution presents a continuous bell-shaped normal distribution curve. It associates with continuous variables such as height, weight, age, fecundity, rate of respiration, HP%, etc. 2. There is only one maximum peak unimodel. The normal curve is symmetrical and asymptotic, touches at infinity. 3. The height of the normal curve is maximum at its mean. Hence, the mean and mode of normal distribution coincide. As the peak of the normal curve divides the distribution into two equal parts, the mean and median also coincide. Thus, for a normal distribution, all measures of central tendency, i.e., mean, median, and mode are equal. Mean equals median equals mode. 4. The area between the curve and the two uprights drawn at any point gives the fraction of the total number of observations between these points. 5. Most of the observations are clustered around the mean, and there are relatively few observations at the extremes. 6. The normal distribution curve has a fixed mathematical characteristic feature independent of the scale, unit of measurement, magnitude, and unit of mean and standard deviation. 2. Binomial distribution. The binomial distribution is one of the most widely used probability distributions of random discrete variates. It was introduced by Bernoulli 1680 and is also known as Bernoulli distribution. This process is one where an experiment can result in only one or two mutually exclusive outcomes such as success or failure, male or female, dead or alive, etc. In case of birth of a child. Binomial expansion is p plus q, 2 equals p2 plus 2pq plus q2. In case of 3 births, we may get 3 male, 3 female, 2 male plus 1 female, 2 female plus 1 male. This can be expressed as follows. Binomial expansion is p plus q, 3 equals p3 plus 3p2q plus 3pq2 plus q3. According to the different values of n, following expansion of p plus q, 2n can be obtained. Probability distribution given by above equation is called binomial distribution. Value of x in above equation is 0, 1, 2, 3, n, then. P1 equals chance of 1 success of probability equals NC1 P1 Q1 P2 equals chances of 2 success of probability equals NC2 P2 Q1 2 P3 equals chances of 3 success of probability equals NC3 P3 Q1 3P R equals chances of R success of probability equals NCR PR Q and R, etc. It means these probability have been taken by the expansion of Q plus Pn in serial steps. Q plus Pn equals Qn plus NC1 P1 Q1 plus NC2 P2 Q2 plus NC3 P3 Q3. NC and Pn R. Formula for the determination of probability in a binomial expansion. In n trials, the total number of possible ways of getting R success and failure NR is probability R successes out of n trials. PR equals R NR PQ R NR. N minus 3. Poisson distribution. In binomial distribution, we study the possibility of events occurred and not occurred. But there are certain events in which possibility of events occurred is only important. For example, in a football match, how many goals scored is important. Death due to heart attack in a year in a hospital or town or country is only reported. Poisson 1837 gave this distribution for a discrete probability distribution. Poisson distribution tells about the probability of rare events. Poisson distribution is made use of in such cases where event occurred, i.e. part is very small. Therefore, I, this is the limiting distribution of binomial distribution when the number of trials is very small and the probability p of success for every trial is also very small. The NP is a fixed number which is called Poisson distribution. This distribution obtained is limited in case of binomial probability distribution under the following conditions. I, the Poisson distribution is a discrete distribution. The Poisson distribution has a single parameter which is the mean of the distribution and is denoted by m. The NP equals m which remains constant. Formula used is as follows. Probability of R success PR equals 1 m RE m minus where p equals probability. R equals 0, 1, 2, 3, n successes. E equals 2.7183 constant. Both binomial and Poisson distribution are discontinuous distributions which are concerned only complete numbers. For example, number of persons in a family, number of death or birth in a hospital. But we come across a number of biological measurements where the variables are continuous in nature and they can be adequately described only by continuous probability distribution, i.e. normal distribution. 41.8 correlation. Many statistical analyses are concerned with problems in which items consist of pairs of measurements. We come across such measurements in biological experiments. When two series of measurements are made at the same time or on the same organism, it is frequently desirable to know whether a relationship exists between variables or not. For example, a biologist may be interested in knowing the relationship between the height and weight of human being or other animals or plants. A doctor may be interested in knowing the relationship between the blood pressure and age of man, HP% and RBC's number. An agriculture student may be eager to know the effect of spray of a hormone on yield of a plant, etc. A relationship between two such sets of measurements, such that value of one measurement is affected by value of the other, is described as correlation. The relationship between the two variables is such that a change in one variable results in a change in the other variable is known as correlation. Kinds of correlation. There are 3 kinds of correlations: positive, zero, and negative correlations. Positive or direct correlation. When values of the two variables deviate together, then the condition is known as positive correlation. For instance, if we say body weight is increasing with the increase in height, relationship is positive 1. Both positive and negative type of correlation may be represented graphically and mathematically. 1. Perfect positive correlation. The two variables denoted by x and y are directly proportional and fully correlated with each other in case of body length and body weight of fish or any living being. Both variables rise and fall in the same proportion. Examples of perfect or total correlation is very rare in nature, but some approaching to that extent are such as body weight and height, age and blood pressure, age and IQ, etc. The imaginary mean line rising from the lower ends of both x and y axes forms straight line. When scatter diagram is drawn, all points fall around the mean line big A. Values of correlation coefficient R is 1 in perfect plus fake correlation. 2. Moderately positive correlation. The two variables denoted by x and y are partially positively correlated in case of age of husband and age of wife. Other examples of partial positive correlation are infant mortality rate and poverty, tallness of plants and the quantity of manure used, nutrition and death rate in pregnancy, etc. Value of correlation coefficient R lie between 0 and plus 1, i.e. 0 less than R less than 1. In moderately positive correlation, the scatter will be around an imaginary mean line, rising from the lower ends of both x and y variables big C. 2. Negative or inverse correlation. If one variable increases or decreases and the other decreases or increases, they are said to be negatively correlated. If temperature is increasing and the lipid content of body of a sample animals is decreasing, it is a case of negative correlation. 1. Perfect negative correlation. The variables denoted by letter x, temperature, and y, lipid content of body, are inversely proportional to each other, i.e. when one x rises, the other y falls in the same proportion. The correlation coefficient R equals -1 to O. Examples of perfect negative correlation is also very rare in life science, but some approaching to that extent are such as blood pressure and age, temperature and lipid content of the body, RBC number and HP%, T4 injection and oxygen consumption, etc. Fig B. 2. Moderately negative correlation. The two variables denoted by x, economic condition of state, and y, case of tuberculosis. In this case, values of correlation coefficient lie between -1 and 0, such as income and infant mortality rate, age and vitality in adults, etc. In such moderately negative correlation, the scatter will be around an imaginary mean line rising from the extreme values of variable Fig D. Figure different types of correlation shown by scatter diagram method. A. Perfect positive correlation. B. Perfect negative correlation. C. Moderately positive correlation. D. Moderately negative correlation. E. Absolutely no correlation. 3. Zero correlation. If the variation in one variable has no relation with the variation in the other, the two variables have no correlation or there is zero correlation. No mean line can be drawn which could indicate trend of correlation. X is completely independent of y. Examples are body weight and IQ, HP% and body weight. The points in the scatter diagram of no correlation are so scattered that no imaginary line can be drawn. Fig E. The data obtained from different biological experiments show positive and negative correlation are shown in figure for curvilinear correlation. The correlations of scores of two variables based on some quality shown by curved line on graph is called curvilinear correlation. Above figure 8 shows the correlation between practice and degree of learning, and B shows the correlation between time and degree of retention. Graph A reveals that up to a certain time degree of learning increases with the practice, but after a certain limitability of learning falls even if practice remains the same or continued. Graph B indicates that correlation between time and degree of retention is represented by curve line. It indicates that with the lapse of time, power of retention memory decreases up to a certain limit. After that memory, even faint, remains present although time passes. Properties of coefficient of correlation. One correlation coefficient lies between L and +1, i.e., -1 is less than or equal to R is less than or equal to 1. 2 if R equals +1, the correlation is perfect and positive if R equals -1, the correlation is perfect and negative. 3 if R equals 0, there is no correlation between the two variables. 4 the coefficient of correlation is not affected by change in scale of origin. Methods of studying correlation. There are 3 popular methods of studying correlation between two variables. Scatter diagram. Scatter diagram is a graphical method of showing the correlation between the two variables. Let x1, y1 I equals 1, 2, and be of the variate distribution. The values of the variable x are plotted along the x-axis and that of y are plotted along the y-axis, corresponding to every ordered pair x1, y1. We have a point in the coordinate plane. The diagram obtained by plotting these endpoints is called the scatter or dot diagram. Merits and demerits of the scatter diagram method. Scatter diagram method is simple device to find out the nature of correlation between the two variables. This method gives the idea about the direction of correlation. It also gives an idea about the nature of correlation, whether it is low or high and whether it is positive or negative. But we cannot get the exact degree of correlation between the two variables, as it is possible only by the coefficient of correlation. This method is not influenced by extreme items. It is the first step to find out the relationship between two variables. 2 Carl Pearson's coefficient of correlation. When the relationship between two sets of variables can be described by a straight line, then the correlation between variables may be expressed by the product moment coefficient of correlation Rx, y or fx, y. The degree of the extent to which the variables of the variate distribution are related with each other is called the coefficient of correlation, designated by the letter R. Carl Pearson 1867-1936 suggested a mathematical method for measuring the closeness of the relationship between two variables. Pearson's measure known as Pearson's product moment correlation coefficient between two variables x and y, usually denoted by Rx, y or Rx, y or simply R. In biological experiments, use of correlation coefficient is very significant. According to J.P. Guilford, coefficient of correlation is a single number that tells us to what extent two things are related and to what extent variations in one go with variations in another. Carl Pearson's coefficient of correlation is given by the expression. In language, we can say that R can be calculated by dividing the sum of products of deviations from the square root of the products of the sums of squares of deviations of the two variables. Here R equals correlation coefficient x equals deviations of x variable, y equals deviations of y variable. 3 rank correlation. Sometimes statistics face statistical series in which the variables under consideration are not called a quantitative measurement but can be arranged in serial order. This happens when we deal with qualitative characters such as color, fecundity, stress, tolerance, etc., which cannot be measured quantitatively but can be arranged serially. Charles Edward Spearman 1904 developed a formula which helps in obtaining the correlation coefficient between the ranks of n individuals in two characteristics under study. Suppose we want to find if two characteristics A, say, color of flower, and B, say, fragrance of the flower are related or not. Spearman's rank correlation coefficient, usually denoted by P rho, is given by the formula. Where P rho is the rank difference of x and y variables, D is the difference between the pair of the same individual and the two characteristics, and n is the number of pairs. Sigma D2 is summation of square of difference of two variables ranked I and 2 R1 and R2. D.9 Regression analysis. In the year 1877, F. Galton coined the term regression for the study of parent and son height relationship. He studied the relationship between the height of about 1,000 fathers and sons and came to the conclusion that height of offspring tend to remain in the middle position. He published the results of his studies in a paper, Regression towards Mediocrity and Heredity Stature. Today the word regression is used in statistics in a wider perspective without any reference to biostatistics. The statistical method to find out a relation between two variables where maybe one of functional dependence of one variable on the other. That is the magnitude of one of the variable. The dependent variable is assumed to be determined by the magnitude of the second variable, the independent variable, whereas the reverse is not true. To draw a relationship between observation of two variables, a diagram is plotted in the form of dots called scatter diagram. A straight line is drawn approaching maximum points. The statistical analysis employed to find out the exact position of the straight line is known as the linear regression analysis. The relationship between the independent variable x and the dependent variable r can be expressed in a mathematical form known as the regression equation. The regression expressed by a straight line is called the linear regression equation. In regression analysis, we can estimate or predict the value of one variable from a given value of the other variable. For example, length and weight of animals. We can find out the expected weight of a man or a woman for a given length. In studying the way in which the yield of paddy vary in relation to change of the amount of fertilizer applied, yield would constitute the dependent variable, and the independent variable is the fertilizer. While studying the oxygen consumption of an animal, the rate of oxygen consumption vary in relation to the T4 injection. Rate of oxygen consumption constitutes the dependent variable, and thyroxine T4 the independent variable. Aim of regression analysis. 1. The meaning of regression analysis is to predict the value of one character of variable, say y, from the known value of the other variable, say x. The former value y to be predicted is called dependent variable, and the latter known variable x is called the independent variable. This is done by regression line and called regression coefficient. Regression line explains the mean relationship between x and y variables. 2. Another aim of regression analysis is to find out measures of standard error. Kinds of regression analysis. There are 4 kinds of regression analysis. 1. In simple regression, there is only one independent variable. 2. In multiple regression, there are 2 or more independent variables. 3. Linear regression can be represented graphically by a straight line. 4. Nonlinear regression forms a curve and is also called curvilinear regression. Linear regression analysis. When two variables x and y are plotted on a scatter diagram, the two lines of best fit can be drawn, which pass between the plotted points. These lines are called regression lines, and the two equations based on these two lines are called regression equation. The statistical analysis employed to find out the exact position of the straight line or lines is known as the linear regression analysis. The two variables have linear relation when change in the independent variable x brings change in the dependent variable y. The most important thing about the regression analysis is to predict the value of one variable by using the known value of the other variable. Regression lines. Composition of regression lines is based on least square assumptions. The general condition for regression analysis is based on the summation of squares of deviations of observed values of y from lines of the best fit is least. It is called least square error. A line of regression gives the best average value of one variable from any given value of the other variable. In regression analysis, there are usually 2 regression lines to show the average relationship between x and y variables. Thus, one regression line shows regression of y upon x and the other shows regression of x upon y when there is perfect correlation, positive or negative IER plus or minus 1. The two regression lines will coincide with each other and will become only one line. Perfect correlation is a rare phenomenon in biological experiments. When regression lines are near to each other, then there is high degree of correlation between x and y. X equals O. It means both the variable are independent and both the lines will kiss each other at right angles. The regression lines, when cut each other at the points of means of x and y, and if the perpendicular is drawn from the point to the x-axis, it will touch the axis on the mean value of x. Similarly, if another perpendicular is drawn from the points to the y-axis, it will touch the axis at mean value of y. Less the correlation greater will be the divergence of angles. Steepness of the lines indicate the extent of correlation. Closer the correlation greater is the steepness of regression lines x and y, y and x. Regression equations. Algebraic expression of the regression line is called regression equations. In other words, expression of relationship between the independent variable x and the dependent variable y can be expressed in a mathematical form known as the regression equation. Regression equation of y on x indicates the changes in the values of x for changes given in y. Likewise, regression equations of x on y indicates the changes in the values of y for changes given in x. Since there are 2 regression lines, there are 2 regression equations. These regression equations are as follows. Regression equation of x on y, xy equals a plus y. Regression equation of y on x, yx equals a plus bx. Here x and y are the variables whereas a and b are unknown constants. The constant a is the distance between the point of origin and the points where the regression line touches the y-axis. The constant b shows the slope of the line and is also called regression coefficient. It indicates that for every 1 unit change in x there will be 2 unit changes in y. The constant a and b can be obtained by the following formula. A equals y dx, where x and y are their respective means. Procedure of the test. One plotted graph between two variables taking independent variable on x-axis and dependent variable on y-axis. Find out the values of a and b given earlier. For drawing the line of best fit regression line, find out any 2 values of y associated with corresponding x by using the equation y equals a plus bx. 2 plot these 2 obtained values on the graph. 3 make a straight line intersecting through these 2 points to get regression line. D10 Analysis of variance a and OVA. In statistics, analysis of variance ANOVA is a collection of statistical models and their associated procedures which compare means by splitting the overall observed variance into different parts. The initial techniques of the analysis of variance were pioneered by the statistician and geneticist R. A. Fisher in the 1920s and 1930s, and is sometimes known as Fisher's ANOVA or Fisher's analysis of variance, due to the use of Fisher's F distribution as part of the test of statistical significance. There are 3 conceptual classes of such models. Fixed effects model assumes that the data come from normal populations which differ in their means. Random effects models assume that the data describe a hierarchy of different populations whose differences are constrained by the hierarchy. Mixed models describe situations where both fixed and random effects are present. In practice, there are several types of ANOVA depending on the number of treatments and the way they are applied to the subjects in the experiment. One way ANOVA is used to test for differences among three or more independent groups. One way ANOVA for repeated measures is used when the subjects are dependent groups. This means that the same subjects are used for each treatment. Note that this method is subject to carryover effects. 2 times 2 red, 2 by 2 ANOVA. The most common type of factorial analysis of variance is used when the experimenter wants to study the effects of 2 or more treatment variables. Factorial ANOVA can also be 2 times 2 times 2, 3 times 3, etc. With higher numbers of factors is rarely done because the calculations are lengthy and the results are hard to interpret. Models. Fixed effects model. The fixed effects model of analysis of variance applies to situations in which the experimenter has subjected his experimental material to several treatments, each of which affects only the mean of the underlying normal distribution of the response variable. Random effects model. Random effects models are used to describe situations in which incomparable differences in experimental material occur. The simplest example is that of estimating the unknown mean of a population whose individuals differ from each other. In this case, the variation between individuals is confounded with that of the observing instrument. Assumptions. Independence of cases. This is a requirement of the design. Scale of measurement of the dependent variable is integral or ratio. Normality of distributions in each of the groups are normal. Use the Kolmogorov-Smirnov and Shapiro-Wilk normality tests to test it. Note that the F test is extremely non-robust to deviations from normality. Lindman, 1974. Homogeneity of variances. The variance of data in groups should be the same. Use Levene's test for homogeneity of variances. Logic of ANOVA. The fundamental technique is the partitioning of the total sum of squares into components related to the effects in the model used. For example, we show the model for a simplified ANOVA with one type of treatment at different levels. If the treatment levels are quantitative and the effects are linear, a linear regression analysis may be appropriate. SS total equals SS error plus SS treatments. The number of degrees of freedom, abbreviated DF, can be partitioned in a similar way and specifies a chi-square distribution which describes the associated sums of squares. DF total equals DF error plus DF treatments. Degrees of freedom. Degrees of freedom indicate the effective number of observations which contribute to the sum of squares in ANOVA. The total number of observations minus the number of linear constraints in the data. The degrees of freedom are the number of participants for each group minus 1. This removes the error otherwise produced by the differences in variance of such groups to account for the difference in sample and population variance. Examples. Group A is given vodka, Group B is given gin, and Group C is given a placebo. All groups are then tested with a memory task. A one-way ANOVA can be used to assess the effect of the various treatments, that is, the vodka, gin, and placebo. Group A is given vodka and tested on a memory task. The same group is allowed a rest period of 5 days and then the experiment is repeated with gin. The procedure is repeated using a placebo. A one-way ANOVA with repeated measures can be used to assess the effect of the vodka versus the impact of the placebo. In an experiment testing the effects of expectations, subjects are randomly assigned to 4 groups. Expect vodka receive vodka. Expect vodka receive placebo. Expect placebo receive vodka. Expect placebo receive placebo. The last group is used as the control group. Each group is then tested on a memory task. The advantage of this design is that multiple variables can be tested at the same time instead of running 2 different experiments. Also, the experiment can determine whether one variable affects the other variable, known as interaction effects. A factorial ANOVA 2 times 2 can be used to assess the effect of expecting vodka or the placebo in the actual reception of either. E1. Properties of radioisotopes and her radioactivity. 1. Introduction. The neutrons and protons that constitute nuclei, as well as other particles that may approach them, are governed by several interactions. The strong nuclear force, not observed at the familiar macroscopic scale, is the most powerful force over subatomic distances. The electrostatic force is also significant. Of lesser importance is the weak nuclear force, and the gravitational force which has no influence on nuclear processes. The interplay of these forces is very complex. Some configurations of the particles in a nucleus have the property that, should they shift ever so slightly, the particles could fall into a lower energy arrangement. One might draw an analogy with a tower of sand. While friction between the sand grains can support the tower's weight, a disturbance will unleash the force of gravity and the tower will collapse. Such a collapse, a decay event, requires certain activation energy. In the case of the tower of sand, this energy must come from outside the system, in the form of a gentle prod or swift kick. In the case of an atomic nucleus, it is already present. Quantum mechanical particles are never at rest, they are in continuous random motion. Thus, if its constituent particles move in concert, the nucleus can spontaneously destabilize. The resulting transformation changes the structure of the nucleus, thus it is a nuclear reaction, in contrast to chemical reactions, which involve changes in the arrangement of the outer electrons of atoms. Some nuclear reactions do involve external sources of energy, in the form of collisions with outside particles. However, these are not considered decay. Rather, this is induced fission or fusion. Thus, radioactivity decay is spontaneous phenomenon of emission of particles or electromagnetic radiations from an atom nucleus. Thermodynamic instability of a nucleus leads to spontaneous decay to a more stable nucleus. Nuclear decay is accompanied by emission of alpha, alpha, beta, beta, gamma, gamma, neutron, proton, and even heavier particles. Elements isotopes that are undergoing nuclear decay are called radioactive elements isotopes. Isotopes are different forms of element with varying number of neutrons and atomic mass but having same number of protons. Radioactivity was first discovered in 1896 by the French scientist Henri Becquerel while working on phosphorescent materials. These materials glow in the dark after exposure to light, and he thought that the glow produced in cathode ray tubes by X-rays might somehow be connected with phosphorescence. So he tried wrapping a photographic plate in black paper and placing various phosphorescent minerals on it. All results were negative until he tried using uranium salts. The result with these compounds was a deep blackening of the plate. However, it soon became clear that the blackening of the plate had nothing to do with phosphorescence because the plate blackened when the mineral was kept in the dark. Also, non-phosphorescent salts of uranium and even metallic uranium blackened the plate. Clearly, there was a new form of radiation that could pass through paper that was causing the plate to blacken. At first, it seemed that the new radiation was similar to then recently discovered X-rays. However, further research by Becquerel, Marie Curie, Pierre Curie, Ernest Rutherford, and others discovered that radioactivity was significantly more complicated. Different types of decay can occur. 2. Types of radioactive decay. In the alpha and beta decay, the original parent nucleus and the product nucleus have different atomic numbers. The types of nuclear decay processes and the associated change in the nuclear charge and mass number are given below. A. Alpha decay. A nucleus undergoing alpha decay emits an alpha particle, which consists of 2 protons and 2 neutrons equivalent to helium nucleus. Atomic and mass numbers of the product nucleus are reduced by 2 and 4 units respectively. AZXA4Z2Y plus alpha. E.g. 232 92 228 90 plus alpha. B. Beta decay. Beta decay comprises of one of the following 3 processes: I negatron decay, beta E positron decay, beta plus, and E electron capture EC. In all the 3 processes, charge of the resulting product nucleus differs from the starting nucleus by 1 unit and there is no change in mass number. I in negatron decay, a beta particle electron is emitted along an antineutrino P, and the atomic number is increased by 1 unit. E.g. 132 53 I 132 54 Na plus beta plus B. E in the positron decay, a beta plus particle positron and a neutrino P are emitted and atomic number is decreased by 1 unit. E.g. 22 11 not 22 10 A plus beta plus B. E in electron capture EC, one of the orbital electron of the atom is captured by the nucleus and neutrino is emitted. Here also the atomic number of the product nucleus is decreased by 1 unit. E.g. 172 71 172 70 out of bits plus B beta, beta plus, B and D are non-nuclear particles the moment they are formed, they are emitted. C. Gamma excitation. Alpha and beta decay quite often leave the daughter product nucleus in excited states. When an excited state of a nucleus undergoes de-excitation electromagnetic radiations, known as gamma rays, is emitted. E.g. 6029 company asterisk 6029 co plus gamma. D. Spontaneous fission. It is the another decay process in which a nucleus undergoes spontaneous division into 2 fragments with emission of 2 to 3 neutrons. This is prevalent in isotopes of heavy elements. E.g. 252 98 CFF1 plus F2 plus 3 neutrons, where F1 and F2 are fission products. The radioactivity processes are energetically feasible when the mass of the parent radionuclide is more than the sum of the masses of the product. M parent M prod equals Q greater than 0. Radioactive decay results in a loss of mass, which is converted to energy. The disintegration energy, according to the formula E equals mech2. This energy is released as kinetic energy of the emitted particles. E. Protons and neutrons. Protons are hydrogen nuclei, 1 each plus. Neutrons transfer their kinetic energy through elastic, inelastic, and particle capture processes. In the inelastic collision process with an atomic nucleus, part of the kinetic energy is utilized to excite the nucleus, and the excited nucleus emits radiation, gamma ray photon. Neutrons do not produce ionization directly, but indirectly by ejecting protons of the atomic nuclei of the target material. In effect, the biological effects of neutrons are due to the protons they produce, Np plus E plus V. Summary of different modes of decay. Radionuclides can undergo a number of different reactions. These are summarized in the following table. A nucleus with charge, atomic number Z and atomic weight A is represented as A, Z. Mode of decay participating particles, daughter nucleus. Decays with emission of nucleons. Alpha decay and alpha particle A equals 4, Z equals 2 emitted from nucleus. A4, Z2. Proton. Emission of proton ejected from nucleus. A1, Z1. Neutron emission of neutron ejected from nucleus. A1, Z. Spontaneous fission. Nucleus disintegrates into two or more random smaller nuclei. Different modes of beta decay. Beta decay, a nucleus emits an electron and N. A, Z plus 1. Positron emission, a nucleus emits a positron and a neutrino A, Z1. Electron capture, a nucleus captures an orbiting electron and emits a neutrino A, Z1. Double beta decay. A nucleus emits two electrons and 2 A, Z plus 2. Double electron capture, a nucleus absorbs two orbital electrons and emits two neutrinos A, Z2. Electron capture with positron emission, a nucleus absorbs one orbital electron, emits one positron and two neutrinos A, Z2. Transitions between states of the same nucleus. Gamma decay, excited nucleus releases a high energy photon. Gamma ray A, Z. Internal conversion, excited nucleus transfers energy to an orbital electron and ejects it. A, Z. E2.